Okay, so here we are for the final segment of Chapter 2. We finished off looking at different compounds and we'd worked our way to organic compounds. And so now we're going to be talking about organic compounds or the compounds that are made mainly of carbon. So typically organic compounds will be hydrogen and carbon. We call them hydrocarbons. They also will have oxygen and nitrogen built into them. So we're looking at sugars, amino acids, things like that. You'll have some nitrogen. We'll also be looking at some of the different functional groups of organic chemistry. Oh, lost my train of thought there for a second. All right, so originally these compounds were thought to be only from living organisms, but now it's a lot more general. So again, we call them hydrocarbons. The simplest organic compounds are going to be hydrocarbons. Oh, sorry about that, running the mouse across there, which means they contain only the carbon and hydrogen. Okay, and so here's how it works. We have methane is CH4, ethane is CH3CH3. Now for these structural formulas, we write them this way. What we're assuming here is that you understand the carbons are the ones that are connected to each other. Okay, so the carbons form what we call a carbon-carbon backbone. And then we go to propane. For propane, again, the assumption would be, get this mouse to show up, there it goes, that this carbon is connected to this carbon, and this carbon is connected to this carbon. These two carbons on the end are not connected, so they're separated by the one carbon in the middle. Same thing can be said for all of these, and these are also referred to as straight chain alkanes. So we have alkanes, and then they're hydrocarbons. Now, hydrocarbons break down into alkanes, alkenes, and alkynes. We're going to be looking at all three of these. You can also form, if we add an oxygen, you can form alcohols and ethers. We can form what's called a carbonyl, which is a C double bond O. And from the carbonyl, we can make several more functional groups. And then if we add nitrogen into the mix, we can start to add even more functional groups. Now, again, we're not going to spend a whole lot of time on organic chemistry because that's a 2-semester full year course that follows general chemistry. So in our 150, 151 series, next would be the 240, 241 series. And so organic chemistry would be a whole nother year, and we're not going to try to compact that into 10 minutes on segment number 5 of chemical naming. It's just not going to happen. So again, if we use our models here, you can see that we have the methane, so it's a tetrahedral is what we're trying to represent there. It's not 90 degrees, it's not a box. Next, you can see in the ethane, we have the two carbons connected to each other. And finally, the propane, you can see that the two carbons on the ends do not touch each other. So again, carbon is black, hydrogen is white. Now, C4H10, we looked at this in a balancing equation in I think segment 3. And so you might have caught on that I called it butane, right? So the correct name for C4H10 is butane. So it's think of it as prefixes for the number of carbons. So 1 carbon would be meth, 2 carbon eth, 3 carbon prop. So 4th carbon is bute, not but bute. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec. Right, so very similar to our Greek prefixes with the exception of the first 4. Now I mentioned alkenes. Notice it's a 1-letter difference. So alkane, A-N-E, right, was methane, ethane, propane, and you'll notice they were all single carbon carbon bonds. So single carbon-carbon bonds gave us A and E. E and E simply means we're going to have 2 less hydrogens than our alkanes to make an alkene. And so formula-wise, it would be CnH2 times N. So basically what we're going to do is take 2 hydrogens out of our formula, and that's because we're going to form a double bond. Okay, and in making that double bond between the carbons, we change the ending from A and E to E and E, and we refer to them as alkenes. So ethylene, propylene, butene, things like that. Now the next one we have is alkynes. For alkynes, you notice we changed to Y and E. The nice part is if you think about it as single, double, triple, it's in alphabetical order. A, E, Y, 1, 2, 3, right? And so alkynes, we have even less hydrogen because now we're going to have a carbon-carbon triple bond. So formula-wise then would be CnH2 H2N minus 2. And so something like C2H2 would equal ethine or acetylene. And if you ever used an acetylene torch, that's what you were using. You're using acetylene C2H2. Again, here we place the A and E for Y and E. Okay. And again, we're going through it kind of quick. We're not expecting you to be organic name masters after this, but we want you to have an idea of what you're working with, and that way we can open up the problem situation to more real life like problems. All right, so hydrocarbons are your basic building for organic chemistry. If we start to look at many other classes, we can derive the compounds there. The next one we see is alcohols. So what we'll do is we'll pull a hydrogen off our methane and connect an oxygen to that carbon and then put an H on that. So this is an OH group, but it's not a hydroxide. So what we're going to find out in this semester is that hydroxides are typically basic, but alcohol is not basic. Okay, alcohol is definitely not a basic. That OH group, it acts different in organic chemistry than it does when it's with water. So if it's with water or a metal, that OH works completely different than when it's with a carbon, right? So an OH group is an alcohol, and so we'll change the name to methanol. So rather than having an A and E ending, now we have an OL ending. Okay, so ethyl alcohol is ethanol, right? This is drinking alcohol if you want. We replace the E in the alkane with an OL. Okay, so what is the name then of C4H9OH? So again, if you base it on the carbons, you look at how many carbons are there, that's going to give you your prefix base name, and that's going to be bute. So now we know it's going to be butanol. All right, what is the name of this guy? So we have CH3, CH2, 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 CCH. So we know that we have 1, 2, 3, 4, 5, 6 carbons. All right, so 6 carbons. So is it hexene, heptacarbon decahydrogen, hexane, hexine, or heptene? All right, so here, gotta count it all up. You know it's got to be hex, right? So now you can think about the formula if you want. We know the formula for ene would be Cn, which would be 6, and then 2n for the hydrogen, which means it would be C6H12. But the Y in E was N for the carbon, which would be 6, and then N times 2 minus 2, which would be 12 minus 2 would be 10, and that's our formula. And so this must be hexine. All right, so writing formulas for organic compounds, well, they're molecular formulas, so it indicates the number of each type of atom in the molecule. So C2H6 for ethane, or C3H8 for propane. The order of the atoms, carbon, hydrogen, and then other atoms would be alphabetical. So carbons are always first, followed by hydrogen. So if I was going to write out sucrose, for instance, C, then H, then we go in alphabetical order after that. In this case, we only have oxygen, so oxygen would be last. Okay. If you have an alcohol group, you'll emphasize that alcohol group. So we'll pull that out. So it's C2H5OH. Now it looks like we could write it as C2H6O. And then there's some cases, especially when we do empirical formulas, we might do that. But if we know the structure is an alcohol, then we like to keep that alcohol isolated. So we would say C2H5 and then have the OH by itself. And a structural formula will indicate how many carbons are connected. So the ethane, for instance, would be CH3CH3. But propane, we showed a CH3CH2CH3. So we're isolating each one of those carbon groups, right? And we call this a condensed formula. Octane is a hydrocarbon with 8 carbon atoms. That is a major component of gasoline. What is the correct molecular formula for octane? Now remember, so if it's the A and E ending, then it's CnH2n plus 2. So if we have 8, then it would be 8 times 2 would be 16 plus 2. And so our answer should be C. All right. What is the correct structural formula for octane? Well, we know it's 8 carbons in a row. So let's make sure we have 8 carbons. We have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So we know it cannot be B. Even though this one's 8, it can't be C because it wants the structural formula, which means we have to show how it's laid out. So we know it's either A or anything else. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's not going to happen. And right away I see the alcohol here, which means my answer has to be A. All right. So again, you're not going to be organic name masters at this point, but hopefully, when you're doing problems, we can actually do some real world problems. A lot of times I'll give you the name and then comma and then give you the formula as well. So that way you can still do the problems that I'm asking you to do, but we can use the real names and the real items and the real problems, if you will, of the world. All right, so nomenclature of molecular compounds. Your goal here is to translate clearly into molecular formula. So how do we name binary molecular compounds? Well, it's going to be based on which two elements are present, and of course how many of each. So our format then is going to be the first element in the formula. We'll use the English name for that. Then we'll have the second element in the formula, and we'll end it in "ide." I don't know why we ended in "ide." No one's ever explained that to me. It just seems a lot of confusion there, because then you're going to mix match with this with ionic naming, because everything's ending in "ide." All right, now we'll use Greek number prefixes to specify how many of the atoms are there. So remember, our name has to tell us what is there and how many is there. Since we don't have charges, we can't do crisscross or any of those types of things to figure out what's there. So the way we do that is with a prefix. Now, how do I do this then? Well, we have hydrogen chloride, so we have HCl. Right? Phosphorus pentachloride, so we have phosphorus. And then pentachloride is 5 Cls, and so PCl5. Triselenium dinitride. So that means I have 3 selenium, 2 nitrogens, Se3N2. Now mono always omitted on the first element. So notice we didn't say monohydrogen, monophosphorus, right? We always do that. Now often omitted on the second element unless more than one combination of same two elements. So in other words, carbon monoxide, right? So we do put the mono on the second element, but not the first. Carbon dioxide. Now, what you might have noticed with carbon monoxide is if the prefix ends in a vowel similar to the start of the element name, we drop the prefix vowel from the prefix, okay? So make sure you drop the last vowel off the prefix, not off of the main name. You'll see this mainly with oxygen, right? Because we can get mono-oxide. It forms that extra syllable, which for whatever reason chemists don't like. So we get rid of that extra syllable. If it's dioxide, the IO doesn't make a long vowel sound. So notice that we just let it go, dioxide, right? But if it's an AO, again, you'll get a long vowel sound. So pentaoxide, we get rid of the A and we call it pentoxide, right? So we just cut the A off of the prefix and then roll into the oxide name. All right, so name each of the following. So we have name the number of the prefix plus the first element name, number of the prefix plus a stem plus ide for the second element name. So AsF3, right? Since As is by itself, it's simply arsenic. And then the fluorine, there's 3 of them, so it's trifluoride. All right, so I'll give you a chance to pause here. Go ahead and work these out. And then I'm going to go ahead and go through them kind of quick with the idea that you've already worked on them and you have something written down, and I'm not waiting for you to catch up for each one. All right, so if you've pushed play, then here we go. If you didn't, and you didn't heed my call here to pause it so you can practice, then you're about to go fast here. So HBr becomes hydrogen bromide. N2O4, we have 2 prefixes. We have the di for the nitrogen and then tetra for oxide. But remember, we cut that A off. So we get dinitrogen tetroxide. N2O5, we have that long vowel sound again. So we're going to cut that A off of our penta prefix for the oxygen. Dinitrogen's the same. So dinitrogen pentoxide. CO, you probably already know, carbon monoxide. CO2, you probably know this one as well, carbon dioxide. All right, let's do some practice problems and finish this up. So, which is the correct formula for nitrogen triiodide? Nitrogen triiodide. The answer is B, right? One nitrogen, because we didn't say mono, and we don't have any other prefix there. So nitrogen, and then three iodines means triiodide. Which is the correct name for P4O10? P4O10. So we know we have 4 phosphorus. The prefix for 4 is tetra. So it's going to be tetraphosphorus, which means it's either going to be C or D. And then 10 oxygen would be decoxide. So our answer is C. All right, which is the correct formula for disulfur decafluoride? Disulfur decafluoride. And the answer is C again, S2F10. All right, last but not least, some exceptions. I told you there's exceptions to every rule. Exceptions to naming binary molecules. So binary compounds of nonmetals and hydrogen. No prefixes need to be used. And you've already seen that. We said hydrogen chloride. We didn't say hydrogen monochloride. All right. You'll get the number of hydrogens for each nonmetal from the periodic table. So hydrogen sulfide would be H2S. Hydrogen telluride will be H2Te. Now we also have molecules with common names. So some molecules have names that predate any of these rules. One of which is water, right? So water is H2O. And then sucrose. A lot of the sugar naming came before any of this. Ammonia and then phosphine. All right, so quick summary of naming here. So a lot of times you can just ask yourself questions because that's what's going to happen. So we've gone through each rule, and typically as students are going through each rule, they're fine with each rule set. And if I gave you all ionic naming, you'd be fine. If I gave you all transition metals, you'd be fine. If I gave you all molecules, you'd be fine. The problem with real life is that we mix it all up. And so once we start mixing it all up, that means you have to be able to keep everything straight. And so the first thing you want to do is ask yourself is, does the compound contain a metal? If you say no, then you know you're going to be using your covalent naming. If you say yes, then you know it's going to be an ionic compound. And then you can ask yourself the next series of questions. Is that metal a transition metal? Now, this flowchart is not one that I've supplied. This is one from your textbook. But if you go under student resources, you'll see one. I have a flowchart up there for naming compounds. And I usually recommend to all my students keep that handy when you're first starting out. Right? So if you're not really getting a grip on naming, you keep that around. Now this one's going to give us a lot more detail than what mine is going to give you. Mine is really good for learning how to name compounds. This one's going to get into breaking down and telling you what is in each compound. So it gives you a little more detail as to rules. All right? So that's going to end our chapter for naming and putting together molecules and elements and all these good things. Next, we'll be taking a deeper look into chemical reactions. So chapter 3 is up next. And if you haven't been able to tell, we're building from little to big. So we started with measurements and numbers and how to do calculations, and then looked at conversion factors and things of that nature. Then we started working on atomic structure a bit. Now we're going to get into a lot more depth with our atomic structure, which is why I was really skimming over here. So later on, we're going to go through a little bit of a history as we develop quantum mechanics. All right. So if you feel like, hey, we missed a few things in here, all you talked about was Dalton's atomic theory, then you're right on cue with that. You're good. We haven't talked about some of these other people yet because they're coming up in a later chapter. From there, we moved into naming, and next we're going to look at chemical reactions. All right. So stay tuned for more chapters, and have a great week.